gentlemen, before I get into the meat of this presentation, I wanted to take some time and have you take a look down by that bell and that ding and that subscribe over here. Please take a moment. Thanks. And just subscribe. We want to make sure that we're getting you all the updated information. We got a lot of things coming out every single day that can help you make your concrete stronger and last longer. And ultimately what we're trying to do is save the world with all the concrete in it, and that is due in part because we care not only about the concrete industry but the concrete in this great nation. So what we're going to be talking about today is the continuation of this hydronic heating project and why we did it. It was a pain in the butt. There was a lot to do. If I was a contractor and I had to do this on a job site, let's say a 20 by 30 foot residential slab, it would take more time than what we put into doing the 3 foot by 3 foot slab, which didn't take a lot of time. It was easy to set up. That being said, the ultimate question is this system, while it is a great idea to help you save, maybe not a major project for some of the larger companies out there, but a major project for a smaller company or a company that has a lot of projects going on at one time. And the idea is that concrete was placed, let's say a residential slab, 5 of them were placed in an evening or in a day, and weather changed all of a sudden from what would have been a 30-degree evening to a -20. It was a cold snap. And what can you do besides just throwing some blankets on to protect that slab and make sure you don't get any lawsuits down in the future? And what we did is set up this job site where we placed it early in the afternoon, and that night it went down to -20 degrees. One slab did not get any protection. The other slab got this hydronically controlled temperature environment, and in that we had a water tube that was circulating heated water between an insulating blanket, and we kept that there for 16 days. Now that's a lot, but the more you can keep it on there, the better. And the question is it worth it? Maybe I should backtrack, get some time-lapse footage over here of Steven coring out the samples from those 2 slabs that we cast, and we cut out 6 samples, 2-inch diameter, and we cut them down to 4-inch tall samples, and we chose 3 of the best out of those 6. And we'll be breaking those and showing you the strengths. But when we take a closer look at the sample where we controlled the temperature, you can see that it looks like concrete from a normal residential slab where you have a homogeneous mixture of your rock and sand. You don't have any paste too close to the surface, and you don't see any segregation of the larger aggregates to the bottom, and it looks like a densified mix with a certain amount of pores, maybe from pore consolidation or just not sufficient consolidation, and then definitely a nice interfacial zone. But all in all, this looks like a good concrete mix or a core sample that was taken out of a concrete slab. You compare that to the sample that was cored out from the slab that didn't receive any of that hydronic temperature controlling, and what we see is a lot of aggregate pop outs. The sample is extremely porous, especially in the paste volume, where you can see some dusting and flaking of that paste. And really that's our ultimate problem here, that because that concrete got down to such a low temperature, we lost that activation energy that ensures those hydration kinetics, and didn't really develop that glue of the concrete composite that holds everything together. And especially in that top surface where that colder temperature really had its greatest impact, we can see that this is a concrete that if it got any abrasion resistance or mag chlorides within its first season, it would surely just fall apart. And this is where the lawsuits start. When a homeowner is rightfully or in their right place to complain about a product that would come from something like this, or a driveway that would come from something like this, and would want it replaced. And as a contractor, if you can have a system that's in a trunk, ready to be used at a moment's notice in the dead of winter, which we should expect this to happen, to create a concrete like the sample that we got from the hydronically controlled temperature, you're going to save that job site and be known as that contractor who can make magic happen even in the dead of winter. So Hopefully you learned something from this. Had a lot of fun doing this project. This cost us a bunch of time, money, and resources, and we were more than happy to do this. And we're gonna keep these samples here in our lab just in case anybody comes out to visit. We can go ahead and refer to them back on this. And I think, so what we did is we put temperature loggers in there so we can see the difference in maturity, because this is what we're doing is, maturity week over here. And as you can see from these maturity curves, so what we've got in front of us is a graph with two sets of curves on it. One for temperature over time, and the other one is maturity over time. This goes back to our maturity conversation, and reason we were using this for that hydronic experiment is we wanted to show two things. First of all, the slab that got that hydronic temperature controlling system during the first 24 hours through the next 16 days, it got to achieve its design temperature. We kept it at that 60 to 78 degree range within the first 24, 48, and 72 hours. And that blue curve, which is that hydronic slab, it looks like a normal slab that you would see on day-to-day concrete operations. That being said, the orange line, which represents that slab that froze, we didn't really get a chance to develop that activation energy to see those thermokinetics of cement hydration. Our lowest temperature was somewhere around 12 degrees Fahrenheit. I mean, with that, we really didn't get a chance to develop that binder matrix strength to give us that concrete that's going to be stronger and last longer. And if you want more proof of that, it goes back to the maturity of the concrete. When we look at the slab that the hydronic system had, you can see that those maturity hours goes well above 4,000 in our 16-day period. The problem with our freezing slab, because we didn't get that activation energy, because we didn't set off that heat of hydration, we're not getting that maturity to achieve the same strength and durability that we were going to rely on for that job site. So again, another great reason to use that maturity system, especially when we're looking at the difference between saving the slab and having to rip it out and replace it. So just ran those brakes, and as you can see, there were two totally different sets of cylinders that we were being broken in the machine. That first set, that brake that just totally exploded at 16 days, got 6,020 PSI compressive strength. Compared to the second set of cylinders that just kind of crushed and fell apart underneath the weight of the compression machine, it only got 680 PSI. So almost 10 times the difference in strength. And that would mean either owning the job site and moving on to the next, or ripping and stripping and replacing your failed concrete structure. It's a really fun project. So thanks for your time. Let us know if you have any questions, any concrete concerns. Go concrete! Beat asphalt!